Welcome to the A320 navigation lesson. In this lesson, you will learn how the individual navigation systems are used and how they relate to flight management system operation. Aircraft navigation is primarily accomplished through the Flight Management System, or FMS. The FMS has three main operational parts: flight management, flight guidance, and flight augmentation. The FMS is designed to minimize the flight crew's workload by automatically computing the aircraft's present position, providing lateral and vertical navigation, computing various flight predictions, and automatically tuning navigation radios. To accurately navigate, the FMS requires input from systems including two flight management and guidance computers, or FMGCs, the Air Data Inertial Reference System, or ADIRS, two radio altimeters, one marker beacon receiver, the DME, VOR, and ILS receivers, and the Global Positioning System, or GPS. Flight crews control and monitor the flight management system through two independent multifunction control and display units, or MCDUs, the flight control unit, EFIS control panels, the ADIRS control and display unit, two radio management panels, or RMPs, primary flight displays, navigation displays, and the Digital Distance and Radio Magnetic Indicator, or DDRMI. The A320 uses multiple ground-based navigation radio receivers, which include two VOR receivers, two DME receivers, two ILS receivers, and one ADF receiver. These radios are automatically tuned by the FMGC, or can be manually set by the flight crew. Course, bearing, and distance information can be displayed on the pilot's primary flight display and navigation display. Additionally, VOR information is displayed on the Digital Distance and Radio Magnetic Indicator. Each aircraft has two VOR receivers and two DME receivers. Each DME receiver has 5 individual channels, which are used for the DME display and by the FMGC for position updating. 3 channels are used for radio position updating. 1 channel is used for VOR DME display, and 1 channel is used for localizer DME display. VOR information can be displayed on the navigation display by selecting the ROSE VOR mode on the EFIS control panel. Once the DME identification is decoded, the 3-letter ID is displayed in the information block on the ND. The VOR frequency, course, and identifier display in the upper right corner. Course deviation information is also shown. If the ground-based transmitter fails, the VOR needle on the ND is removed. The ID changes back to the numeric frequency, and on the DDRMI, the associated needle slews to 90 degrees. If the VOR receiver fails, the ND indication turns red and the DD-RMI displays a failure flag. One ADF receiver is installed. When tuned, bearing information from the ADF can be displayed on each pilot's ND by selecting the number 1 selector switch to ADF. The information block on the ND displays the tuned frequency. After the Morse code has been decoded, the station ID is displayed. If the receiver fails, a red ADF flag is displayed in the information block on the ND. Two ILS receivers are incorporated within two multi-mode receivers. The multi-mode receiver integrates an ILS receiver and a GPS receiver into a single unit. These receivers display tuned ILS information on both pilots' PFD and ND. Information from ILS-1 is displayed on the captain's PFD and the first officer's ND. ILS-2 information is displayed on the first officer's PFD and the captain's ND. On the PFD, an amber ILS indication will flash to indicate that an ILS approach has been initiated. However, the ILS push button has not been pressed. Press the ILS push button. ILS information is now displayed on the respective PFD. Notice the localizer and glide slope deviation scales. The ILS identifier and frequency are displayed in the lower left corner. The DME distance is also displayed if the ILS has a co-located DME. The localizer course is also displayed on the heading indicator. ILS information can also be displayed on the navigation display by selecting the ROSE ILS mode on the EFIS control panel. Localizer and glide slope deviation indicators are shown. The ILS frequency, course, and identifier display in the upper right corner. If an associated receiver fails in flight, red warning flags are displayed. One marker beacon receiver is installed in the VOR-1 receiver. When a marker beacon signal is received, the marker beacon symbol is displayed on the PFD and a tone is broadcast. A blue OM is used to depict an outer marker. An amber MM for the middle marker. And a white airway is displayed for the inner marker. Marker beacon audio volume is controlled by the marker reception knob on the audio control panel. There are three different methods to tune the navigation radio receivers: automatically by the FMGC, manually with the MCDU, or by using the standby nav function on the radio management panels, or RMPs. The navigation radios are primarily controlled by the FMGCs. The FMS automatically tunes the navigation radios and uses them for localizer guidance during takeoff, FMS position updating, en route VOR DME display, and ILS VOR and ADF approach guidance. Each FMGC tunes its respective navigation radios. If either FMGC fails, the other FMGC will automatically take over and tune all nav radios. Nav aids that have been tuned are displayed on two separate MCDU pages. The radio nav page displays the nav aids that have been tuned automatically or manually for display on the NDs. The selected nav aids page lists the nav aids that have been tuned for radio position updating. There are two methods to manually tune a nav aid. The first method is to enter the identifier into the scratchpad and insert it in the desired field. Notice that the identifier appears in large font, indicating it is being manually tuned, while the respective frequency is displayed in small font. The second tuning method is to enter the nav aid frequency into the radio nav page. Once a nav aid has been manually tuned, it will remain tuned until it is cleared by the pilot. If a specific course is desired, it can be typed in the scratchpad and entered in the course field in the second line. The tuned VOR information can be displayed in two ways. Using the VOR ADF selectors on the EFIS control panel to display the bearing pointers, identifiers, and DME distance on the NDs. Or using the ND rows VOR mode to display the standard HSI type instrument with CDI and deviation scales. Once cleared, the FMGC resumes auto-tuning as indicated by the small text. In the event that both FMGCs or both MCDUs fail, the radio management panels can be used for nav aid tuning. The captain's RMP tunes the number 1 ILS, VOR, DME, and ADF radios. The first officer's RMP tunes the number 2 ILS, VOR, and DME radios. Let's discuss the steps necessary to tune a nav aid using the RMP. Selecting the guarded nav button on the RMP enables standby tuning. The green light next to the button indicates that standby tuning is active. The desired nav aid can now be selected by using the standby nav buttons. The frequency is tuned in the standby window and moved to the active window by pressing the frequency transfer button. The desired course can now be set. The VOR is now tuned with the proper frequency and course in the RMP. When a VOR or ADF frequency is tuned with the RMP, an R is displayed next to the frequency on the ND. Note that it is possible to set the VOR frequency, an ILS frequency, and an NDB frequency. The RMP will retain these frequencies even when a different radio is selected. The Air Data Inertial Reference System, known as the ADIRS, is comprised of 3 individual Air Data Inertial Reference Units, known as ADIRUs. Each ADIRU is separated into Air Data Reference Information, known as ADR, and Inertial Reference Information, or IR. The IR portion of each ADIRU is responsible for determining the aircraft's present position, attitude, and ground speed. The ADR portion of each ADIRU receives information from the pitot-static system and determines barometric altitude, temperature, and airspeed. The 3 ADIRUs provide information to different users. ADIRU-1 generally provides data to the captain's displays. ADIRU-2 generally provides data to the first officer's displays. ADIRU-3 is held in standby for use when either of the other ADIRUs malfunctions. The ADIRS is mainly controlled through the MCDU, but can also be controlled using the Control and Display Unit, or CDU, located on the overhead panel. The 3-position mode selector switches on the ADIRS CDU are used to align and depower the individual ADIRUs. In OFF, the ADIRU is not energized, so ADR and IR data is not available. NAV establishes power, initiates the alignment, and is the normal setting for operations. Attitude is used during malfunctions to try to restore some functionality to the ADIRU. Also located on the ADIRS CDU are 3 ADR push buttons and 3 IR annunciators. The ADR push buttons control power supply to their respective ADR. The ADR push buttons also include an integral amber fault light to signal a problem with that ADR. The IR annunciators contain amber fault lights and white align lights. The fault light illuminates steady if the IRU has experienced a total failure and cannot be recovered. A flashing fault indicates that the IRU has lost its present position, but attitude and heading may be restored through an air alignment. Each IRU uses a set of ring laser gyros to sense rotation about the 3 axes, pitch, roll, and yaw. Accelerometers are used to sense lateral and vertical displacements about the same axes. By constantly monitoring movements and accelerations, each IRU will sum these displacements to determine present position, aircraft attitude, true heading, track, ground speed, vertical speed, and a wind value. Although IRUs are very accurate, the accuracy does degrade over time due to errors in the system. Each ADIRU has 2 power sources, a normal 115-volt AC power source and a backup 28-volt DC power source. When a unit is selected to nav, it is connected to the battery to test the backup power source. While connected to the battery, the on-battery light illuminates. After 5 seconds, if no faults are detected, the respective ADIRU will connect to its normal AC power source, and the on-battery light extinguishes. Normal power for ADIRU1 is from the AC essential bus. This ensures that ADIRU1 will be powered when the electrical system has downgraded to the emergency electrical configuration. ADIRUs 2 and 3 normally receive power from the main AC buses. Should AC power fail, the batteries provide backup power to all 3 ADIRUs. Once the emergency generator is online and the AC essential bus is repowered, ADIRU1 operates normally. If after 5 minutes, AC power cannot be restored to the main AC buses, ADIRUs 2 and 3 are disconnected from the battery and remain unpowered for the remainder of the flight. The 3 ADIRUs must be aligned before they can function. Alignment must always be accomplished with the aircraft stationary. During alignment, the IRU determines aircraft attitude, latitude, and true heading. Alignment is initiated by selecting the respective ADIRU mode selector from off to the nav position. When nav is selected, a 10-minute alignment process begins and the respective align light illuminates. Additionally, the memo message, IR in align greater than 7 minutes, is shown on the left side of the memo section. This message begins a countdown at 7 minutes and will turn amber if an engine is started before alignment is completed. This notifies the crew that the aircraft cannot be moved until alignment is complete. While it is not necessary to monitor the alignment process, there are flight deck indications of progress. The DDRMI displays heading and VOR flags until the alignment process is complete. On the ND, the message "Map Not Available" is displayed until the aircraft position is computed. The PFD displays a red attitude flag until the IRU determines the aircraft attitude, and a red heading flag until the system determines the magnetic heading. The IRU determines the aircraft attitude approximately 30 seconds after the alignment has been started. At that time, the PFD horizon indication appears with a red flight director flag in view until at least 2 IRUs are aligned. To complete the IRU alignment process, the aircraft present position must be entered. If the present position is not entered within 9 minutes, the align lights will flash and the countdown timer on the EWD will stop at 1 minute remaining. There are 2 other faults that could cause the align lights to flash. The present position entered differs from the position memorized when the IRU was last shut down by more than 1 degree latitude and/or 1 degree longitude, or the aircraft moves during the alignment process. When the alignment is complete, the align lights on the ADIRS CDU will extinguish, and the message IRS in align will appear briefly in the ECAM memo section. After the 3 ADIRU mode selectors have been rotated to nav, the present position may be entered. To enter the present position, first enter the origin and destination airports in the From To fields on the initialization page. The latitude and longitude for the departure airport reference point is retrieved from the active FMS navigation database and displayed on this page. This reference point is located at the approximate airport center and becomes the starting point for IRU navigation. On aircraft without functioning GPS, this position should be modified to the actual aircraft position, such as the gate coordinates. The latitude and longitude fields may be modified by the vertical slew keys on the MCDU to enter the correct coordinates. To modify the longitude value, press the line select key adjacent to the depicted coordinates, which will move the down-up symbol to the longitude side. Again, use the MCDU vertical slew keys to enter the appropriate longitude value. Once the desired values are entered, select the Align IRS prompt to complete the entry of the present position. Provided all other alignment requirements have been satisfied, 1 minute after the position is entered, the alignment will be complete. A full 10-minute alignment is required on the first flight of the day if the previous flight had limited position updating with radio nav aids, such as Class II airspace, or if required by the Airway Manual special pages. If the IRUs have previously aligned and the mode selector switches are in the nav position, a 3-minute fast realignment may be accomplished instead of a full alignment. Fast realignments can only be accomplished if there are no alignment errors and power has not been removed from the IRU. Should an excessive error develop, a full alignment will be necessary. To initiate a fast realignment, select all 3 mode selector switches to off and then back to nav within 5 seconds. Note that as the selectors are moved to off, a 5-second countdown timer is provided on the CDU annunciator with the message, Realignment Decision 5 seconds. If the selectors are moved within the allotted time, the EWD memo IR in a line 1 minute is displayed, indicating the system is accomplishing a fast realignment and is awaiting position data. If the IRU determines that a fast realignment is not possible, it automatically initiates a full alignment. This is indicated by the memo message IR in a line greater than 7 minutes. Fast alignments should be initiated more than 10 minutes before departure in case a full alignment is required. Present position entry during a fast realignment is identical to a normal alignment. The Global Positioning System, or GPS, is a navigation system that uses data from 24 satellites to determine aircraft position. Each aircraft is equipped with 2 GPS receivers. Each GPS receiver is integrated with an ILS receiver in a modular avionics unit called the Multi-Mode Receiver, or MMR. GPS position is processed by the FMGCs to provide a highly accurate aircraft position. The GPS satellites orbit the Earth in a predictable pattern stored in the GPS receivers. Each satellite contains a highly accurate atomic clock and constantly transmits a signal, which includes the time it was transmitted. The 2 GPS receivers monitor the satellite signals and determine the time taken to receive the signal, which yields the distance from each satellite. Present position is automatically determined by triangulating the resulting distances. When the receivers are able to track at least 3 satellites, a 2-dimensional position can be determined in terms of latitude and longitude. When 4 or more satellites are tracked, the aircraft's 3-dimensional position, latitude, longitude, plus altitude can be determined. Ground speed and track are determined by the rate and direction of position change. The availability of GPS signals can be predicted for a given place and time based on the predicted position and status of the GPS satellites. These predictions are computed by a system known as the Predictive Receiver Autonomous Integrity Monitoring, or RAIM. Flight dispatchers monitor the availability of GPS for the anticipated time of arrival using the RAIM system and other computer-based tools. GPS satellite availability can be displayed in the flight deck using the Predictive GPS page, selectable from the Progress page. Predictions are made for 15 minutes before and after the given ETA at the destination and 1 additional airport or waypoint. The identifying numbers of individual satellites which are expected to be unreliable or inoperative at the ETA can also be entered on this page for use in the prediction calculation. The entered satellites are considered inoperative for the purposes of calculating the prediction, but their use is not restricted in actual operation. There are 2 separate GPS system architectures used on A320 aircraft. Older A320s have an autonomous architecture. In the autonomous structure, GPS and IR information is transmitted independently to the FMGCs. The FMGCs prioritize the GPS-derived information, but will apply the IR position if the GPS becomes unavailable. On the MCDU Data Position Monitor page, the position is labeled as the GPS position. Newer A320s have a hybrid architecture. In the hybrid structure, GPS information is sent to the respective ADIRUs for processing. The ADIRUs calculate a combined GPS-IRS position called GPIRS and transmit it to the FMGCs. The Data Position Monitor page shows the GPIRS position. At the core of the navigation system are 2 flight management and guidance computers. These computers have 2 functions: flight management and flight guidance. Flight management functions include lateral and vertical navigation, performance prediction and optimization, flight planning, navigation radio auto-tuning, and generating the navigation information for the flight displays. Information can be entered into the FMGCs by the pilots using the two MCDUs. The captain's MCDU is connected to FMGC1, and the first officer's MCDU is connected to FMGC2. The FMGCs use internal customized databases for navigation and performance calculations. Two navigation databases containing information on navigation aids are loaded into each FMGC. Specifically, the databases contain data including waypoints, navigation aids, airports, runways, holding patterns, airways, and departure, arrival, and approach procedures. Only one database is valid at any time, based upon start and end dates. Database validity can be determined through the data and aircraft status pages on the MCDU. The active database and second database run in a 28-day cycle. If the current data happens to fall within the second database, it can be activated by pressing the line select key adjacent to the arrow. The FMGCs use additional databases which are not accessible to the pilots during normal operations. These databases include a configuration database that can be customized by an airline to allow for factors such as taxi fuel, performance corrections, and fuel reserve policies. A performance database which contains the performance information based on the airframe and engine type, and a magnetic variation database which allows the FMGCs to perform navigation calculations and determine the aircraft's magnetic heading. In addition to guiding the aircraft laterally along the flight plan route, the FMS computes a vertical flight profile to optimize aircraft performance. The flight profile can be broken down into different phases of flight. The flight phases have optimum speeds, calculated by the flight augmentation computers, called managed speeds. If the pilots choose to fly in managed speed by pushing on the FCU speed knob and the autothrust is engaged, the aircraft will fly the optimum speeds for each phase. During pre-flight, the flight crew enters information such as flight plan waypoints, weight data, performance factors, and any speed or altitude constraints. The FMS then computes the optimum flight profile from the departure to the destination airport based on a cost index. The takeoff phase is entered when takeoff thrust is set and continues to acceleration altitude. The managed speed for the takeoff phase is called SRS, which stands for Speed Reference System. SRS equals V2 plus 10 knots for both engines running, or V2 single engine. The climb phase extends from acceleration altitude to the cruise altitude entered in the MCDU. In this phase, the FMS guides the aircraft along the flight plan and commands acceleration when above the terminal area speed restriction altitude. Below 10,000 feet MSL, the managed speed is 250 knots. Above 10,000 feet MSL, the aircraft's managed speed increases to economy climb speed. Economy speeds are calculated using cost index, gross weight, and ambient conditions. In addition, the FMS will observe any speed or altitude constraints entered in the flight plan. The cruise phase of flight extends from the top of climb to the top of descent. It includes any step climbs as well as en route descents. Like the climb phase, the FACS calculate an economy cruise speed using cost index, aircraft weight, and ambient conditions. Once the aircraft reaches the top of descent point, or is within 200 nautical miles from the destination, the FMS will transition to the descent phase. During the descent phase, the FMS calculates the appropriate point to start the descent. It also calculates an economy descent speed, above 10,000 feet MSL. Below 10,000 feet MSL, the managed speed decreases to 250 knots. Like the climb phase, the FMS will honor any altitude or airspeed constraints entered in the flight plan. The approach phase is entered when the pilot activates and confirms the approach phase on the performance page, or when the aircraft reaches the approach deceleration point. In the approach phase, the FMS and FACS calculate speeds depending on the configuration of the aircraft in anticipation of flap and gear extension. With the approach phase activated and the flaps and landing gear retracted, the managed aircraft speed is called green dot, noted by a green circle on the airspeed tape. Green dot is the slowest airspeed the aircraft should fly in the clean configuration. When the pilot moves the flaps handle to the flaps 1 position, the managed speed slows to S speed. At flaps 2 and 3, the managed speed is called F speed. When the flaps are extended to full, the managed speed is V approach. The go-around phase begins when the thrust levers are advanced to toga. The FMS will automatically navigate the programmed go-around procedure. However, managed vertical flight is not available. The pilot must select the appropriate altitude constraints on the FCU. During a go-around, the aircraft will accelerate to green dot in managed speed. This speed anticipates that the flight will either be cleared to hold or to fly another approach. Shortly after landing, the FMS enters the done phase. In this phase, the FMS clears the active flight plan and is now ready for reinitialization. During normal operations, each FMGC performs its own computations and synchronizes with the other FMGC through a crosstalk bus. This is known as dual mode. In this mode, information entered into the MCDU is sent to the corresponding FMGC and is then automatically transferred to the opposite FMGC. Depending on which autopilot is active, one FMGC will be designated the master and the opposite FMGC will be the slave. The two FMGCs will operate independently if a mismatch between the two computers occurs. These mismatches usually occur as a result of software differences, such as navigation databases, aircraft-specific data, or engine types. When independent operation is displayed on the MCDU scratchpad, information entered can only be sent to the associated FMGC. For example, if the flight plan is entered into the captain's MCDU, it will not be transferred to FMGC2 and will not be displayed on the first officer's MCDU. If one FMGC fails, the system will automatically reconfigure to single mode. The operating FMGC continues to provide flight management and flight guidance commands and can be operated using either MCDU. However, the operating FMGC can only generate one navigation display at a time, based on EFIS control panel settings on the operating side. In order to display map data on both nav displays, the EFIS control settings on the failed side should be set to match those of the operating side. In this example, since FMGC1 has failed, the captain's map range should be set to match the first officer's range. In dual mode, aircraft position, gross weight, and target airspeed are computed independently by each FMGC. If these computations differ significantly, a scratchpad message is generated. Under these circumstances, changing the autopilots or any action which changes the master FMGC may result in a corresponding change in aircraft flight path or speed. FMGC malfunctions are uncommon, but can include either a failure or a reset. A failed FMGC will stop sending data and stop receiving inputs for the remainder of the flight. During an FMGC reset or timeout, an error has occurred in the software processing. The affected FMGC will attempt to restore itself. If the restoration is successful, the FMGC will resume normal operation. If the FMGC does not restore itself, pilots may refer to the QRH to attempt to restore function. During ground and flight operations, each FMGC independently uses GPS, IRS, DME, VOR, and localizer signals to compute a present position. The most accurate position is computed based on IRS and GPS information. Should a system fail to provide the required information, position is computed based on system priority as shown here. The Position Monitor page displays the type of position updating available and in use. Now we'll take a closer look at the methods for computing the present position. After alignment, the three individual inertial reference units each calculate a present position, track, and ground speed. These three independently computed positions are blended together by the FMGC to compute a mean position called the mix IRS position. The mix IRS position is displayed on the Position Monitor page. The individual IRS positions are displayed along with the distance in nautical miles from the calculated mix position. If one IRS fails, a mix IRS position is not computed. Instead, the FMGC uses the associated IRS position. FMGC1 uses IRS1, and FMGC2 uses IRS2. IRS3 is automatically substituted for a failure of either IRS1 or 2. During most operations, the GPS signals are used to determine the aircraft's position. On most aircraft, this position is not a pure GPS position, but a hybrid position that combines both the GPS and IRS positions into a combined GP-IRS position. Using this combination of a highly accurate GPS position and a reliable IRS position ensures that the signals sent to the FMS are very accurate and stable. The individual GPS positions can be viewed on the GPS Monitor page. GPS-1 data is displayed on the upper portion of the display, while GPS-2 data is displayed on the lower portion of the display. The combined GP-IRS signal is displayed on the Position Monitor page. When GPS accuracy and integrity requirements are met, GPS primary will be displayed on the MCDU progress page. If the GPS reception is lost due to insufficient satellite coverage or failure of both GPS receivers, the message GPS primary lost is displayed on the scratchpad. When GPS is lost, the FMGCs will automatically reconfigure to radio position updating. Radio position is computed by the FMGC in several ways. Each FMGC automatically tunes 3 DME channels for radio position updating. The FMGC uses 2 of the signals to determine the aircraft's position by the intersection of a DME arc. This position is used to refine the IRS position and is then referred to as the radio position on the FMS. In the event that multiple DME signals are not available, the FMGC will use the IRS position combined with a VOR radial and a DME distance to determine the aircraft's present position. Should the DME receiver fail, the offside DME is used by the affected FMGC to determine radio position. The radios currently tuned for radio position updating can be viewed by accessing the selected NavAids prompt from the Data Key Position Monitor page. Occasionally, individual NavAids are unreliable or placed out of service by NOTAM. By entering the station identifier into the deselect field, the FMGC will not automatically tune the NavAid. Up to 6 NavAids may be deselected from auto-tuning and radio position updating. Aircraft without GPS capability use IRS and radio position updating to determine aircraft position. When on the ground, radio position updating is not active and the IRS is used for FMGC position computation. Because IRS position drifts, this position becomes less accurate over time. During long taxis or if inaccurate gate coordinates were entered during pre-flight, the ND may display the aircraft a considerable distance from the actual location. The difference in IRS mix position and the runway position is referred to as the takeoff bias. Prior to departure, the takeoff runway is entered into the active flight plan. When flex or toga thrust is set, the FMGC position is automatically updated to the end of the entered runway. This takeoff update can be viewed as the takeoff begins, when the airplane symbol on the ND moves to the runway position. If an intersection takeoff is desired, a takeoff shift must be entered for accurate climb profile computation. To enter a takeoff shift, access the Performance Takeoff page and enter the distance from the runway departure end to the intersection point. Once in the air, radio position updating begins and the FMGC position is updated automatically. When GPS and radio positions are not available, the IRS mix position, corrected for any takeoff bias, is used by the FMGCs to determine position. A short time after radio position is lost, the scratchpad message, IRS only navigation, is displayed. For the time GPS and radio positions remain unavailable, the FMGC position is not updated and aircraft position will depend upon the accuracy of the bias-corrected mix IRS position. Once radio position updating is available, the FMGC position is progressively updated. The FMGC continuously monitors the accuracy of its estimated position. Since several signals are used to compute the aircraft's present position, there may be some error between the aircraft's actual position and the computed position. This is referred to as the estimated position error, or EPE. EPE is the radius of a circle around the computed aircraft position with a 95% probability of accurate positional data. The estimated error in position can be viewed on the progress page. The EPE value depends upon the type, frequency, and quality of the position updates available. In addition to monitoring EPE, the system reports the navigation accuracy that is required for a given airspace. This is known as Required Navigation Performance, or RNP. Default RNP values are based upon the type of airspace for en route and terminal area navigation, and upon the approach guidance in use during approach. Default RNP values are 2 nautical miles for en route operations, 1 nautical mile for terminal area navigation, 0.3 nautical miles for GPS and precision approach navigation, and 0.5 nautical miles for all non-ILS approach types. Individual approaches may have an associated RNP value that is different from these default values. In this case, the navigation database RNP value will overwrite the default value when the approach is selected in the flight plan. Since the FMGC continuously monitors accuracy, if the EPE becomes larger than the RNP, the message NAV Accuracy Downgrade is displayed. EPE and RNP can be viewed and compared on the progress page. Note that in this case, low has replaced the word high in the accuracy field. Once the navigation accuracy is restored, the message NAV Accuracy Upgrade is displayed. The majority of FMGC data entry and control is through the associated MCDU. The MCDU is used for long-term changes to the flight management system, such as revising the flight plan, inserting weights, and changing cruise altitudes. The panel is comprised of the display area and associated line select keys, automatic light sensors, annunciators, brightness adjustment control, function and mode keys, and alphanumeric keys. The upper section of the MCDU contains the display area and line select keys. The display is divided into separate functional areas. The title identifies the current page. The label lines are displayed in small font and identify the data directly below. The data line contains the information the FMS uses for flight planning or calculations. Each label and data line has a corresponding line select key located on each side of the display. Line select keys are identified as 1 left through 6 left on the left side of the display and 1 right through 6 right on the right side. Line select keys are used to enter data from the scratchpad to a selected field, activate a function that may be identified by a prompt, or access a submenu. The scratchpad is located at the bottom portion of the display. As information is typed on the keypad, it is initially entered into the scratchpad. It can then be entered into the FMS by selecting the appropriate line select key. In addition to entering information, messages can be displayed in the scratchpad. The MCDU can be used for other functions in addition to flight management. For example, the ADIRS system can be operated from the MCDU. If one of these systems linked to the MCDU has a message, the MCDU menu annunciator will illuminate. The FM annunciator illuminates when one of the linked systems, such as the ADIRS, is in use, and the FMGC has generated a message. In this case, the flight crew should select the FMGC to view the message. The fail annunciator illuminates to indicate that the MCDU has failed. The alphanumeric keys are used to enter letters and numbers into the scratchpad. The slash key is used to separate values that are entered. The clear key can be used to erase messages and information entered in the scratchpad, or to clear data from the display fields. If an entry has been made in the scratchpad, pressing the clear key a single time will erase the last character. Pressing and holding the clear key will erase the entire entry. If the scratchpad is empty, pressing the clear key will display CLR in the scratchpad. Now, pressing a line select key will clear the information adjacent to the key. Frequently during navigation, the FMS will start a turn prior to reaching the waypoint, thus allowing the aircraft to remain within the airway's protected airspace. These waypoints are known as fly-by waypoints. However, certain waypoints must be overflown before the turn can begin. These points are known as fly-over waypoints. If desired, any waypoint on the flight plan can be designated as a fly-over waypoint by pressing the overfly key, then pressing the line select key adjacent to the waypoint. Fly-over waypoints are designated by a triangle next to the identifier. The last key we will discuss on the keypad is the plus and minus key. This key is used when a positive or negative value needs to be assigned to an entry. For example, a negative temperature would be entered as -52 degrees. Screen brightness is controlled on the right side of the panel. Once the desired brightness level is set, light sensors automatically adjust the brightness level for varying lighting conditions. The brightness of the annunciators is controlled by the aircraft's master bright-dim test system. Keypad backlighting is controlled by a separate integral light control. Several colors are used on the MCDU display to identify information. White fonts are used to identify labels and titles as well as certain messages. The active waypoint of the flight plan route is also shown in white. Cyan font identifies data that can be modified by the pilot. Cyan is also used for tuned nav aids. Amber boxes indicate mandatory data is missing. Amber is also used to show that an entered constraint will be missed. Large green font indicates pilot-entered waypoints and other non-modifiable data, while small green font shows computed data associated with the data line. Magenta font is used to signify constraints and the maximum altitude. It also indicates if the constraint will be met. Yellow signifies that you are working with temporary flight plan data. The function and mode keys are located in the center of the MCDU. In this topic, we will give a brief overview of each page. Selecting the MCDU menu key displays the menu page where all of the systems linked to the MCDU are shown. The active system is displayed green, while inactive systems are shown in white. Any system can be selected by pressing the line select key next to the prompt. The vertical slew keys are used to view additional data. For example, the flight plan may contain more data than can fit on the page, as indicated by the up and down arrows. Selecting a slew key moves the listed flight plan entries up or down as directed, allowing for display of the additional data. The left and right arrows indicate that more than one page of data is available. Selecting the Next Page key displays the previous or next page. The data key is used to access various pages related to the aircraft's position and status. The second page of the data index displays information relating to the navigation database. Information pertaining to navigational aids and waypoints can be viewed by selecting the appropriate prompt, then entering the identifier. The flight crew can also enter navigational aids and routes that are not contained in the database by using the prompts on the right side of the display. For example, selecting the pilot's waypoints prompt allows the flight crew to enter a waypoint by using latitude and longitude or by referencing it to an existing VOR. Pressing the initialization key displays Initialization Page A. Initialization Page A is used to enter basic flight plan data during pre-flight. Information such as the route, flight number, cost index, cruise altitude, and the destination and departure airport can be entered. Initialization Page B displays modifiable fuel information that the FMS uses to fine-tune the fuel predictions. Additionally, the CG and zero fuel weight are entered on this page. The fuel prediction page displays fuel and time information, including gross weight, center of gravity, and fuel on board. The first two lines provide predictions of estimated time of arrival and estimated fuel on board for the destination and alternate airports. Additional fuel and time predictions are based upon the active flight plan, the dynamic gross weight, and fuel on board. Pressing the PERF key displays the performance page for the current phase of flight. The various performance pages display data, predictions, and speeds for each flight phase. During pre-flight and taxi, the takeoff page is presented. V-speeds and a reduced power takeoff flex temperature are entered on this page. In addition, default thrust reduction and acceleration altitudes, which are automatically entered by the FMGC, can be modified by the pilot. Once an aircraft weight has been entered into the MCDU, the FMGC will calculate minimum performance speeds. After takeoff, the climb page is displayed. During flight, the cost index can be modified as required to increase performance or adjust fuel burn. The time and distance required to climb to the altitude set in the FCU are displayed on this page. Predictions based on a climb using the Expedite push button on the FCU are also provided. When the cruise altitude set in the FMGC is reached, the cruise phase becomes active. On this page, predictions to the destination airport and top of descent are displayed. Once a descent is initiated, the descent phase becomes active. On the descent page, time and fuel predictions to the destination are displayed. In certain cases, the pilot can view the flight phases by pressing the previous or next phase prompts. Similar to the takeoff page, the approach page allows the flight crew to enter information used to calculate the aircraft's approach performance. Environmental data at the destination airport, such as ADIRS, can be entered. The selected approach is displayed, with either an MDA or DH entered by the crew. Calculated approach speeds are also presented. The approach phase is commonly activated by selecting the Activate Approach Phase prompt from the Active Flight Phase page. If the thrust levers are moved to toga during approach, the aircraft will enter the go-around phase. The PERF page will display the F, S, and green dot speeds, along with the thrust reduction and acceleration altitudes. Pressing the PROG key displays the progress page, where dynamic flight information and other data related to the flight are displayed. Much like the PERF pages, the information on this page is dynamic based upon the current phase of flight. The optimum and recommended maximum altitudes are displayed on this page, and if desired, the cruise altitude may be manually adjusted. The report prompt provides access to a pre-formatted report page, where flight plan information is stored in an ICAO position report format. Select the PROG key to return to the progress page. The Update At field allows you to manually update the FMGC position in flight. Line 4 of the progress page allows you to enter any waypoint or nav aid and determine your magnetic bearing and distance to the fix. GPS status is also displayed on the PROG page. Selecting the F-Plan key displays Flight Plan page A, where a leg-by-leg description of the active route can be viewed. The title line contains the flight number, and left and right arrows signifying that another page is available. The From waypoint is shown at the top of the flight plan with the active or To waypoint shown in white. Each individual waypoint is listed along with the route. To the right of each waypoint is the estimated time of arrival, speed, and altitude at the waypoint. On Flight Plan page B, notice that the data labels and information in the columns change to estimated fuel on board and wind. The bottom line is reserved for the destination airport, with predictions for estimated time of arrival, distance remaining, and estimated fuel on board at the arrival airport. By pressing the up or down slew keys, you can scroll through the entire active flight plan. Regardless of where you are in the flight plan, pressing the flight plan key will return to the top of the flight plan, with the From waypoint listed at the top. Lateral and vertical revisions to the flight plan are controlled by the 2 rows of line select keys. Selecting a left side key will display the lateral revision page for that waypoint. On this page, you can program the FMS for holding, enter latitude-longitude crossing points, select the next waypoint to be flown, or enter a new destination airport. Select the Flight Plan key to return to the Flight Plan page. The vertical revision page is accessed by selecting the right side keys. From this page, you can access the required time of arrival and step altitude pages. Speed and altitude constraints can also be entered or changed. The secondary flight plan allows the crew to enter an additional flight plan into the FMGC. This gives the flight crew the flexibility to add route modifications or different instrument approaches without making the change directly into the active flight plan. At any time during the flight, the active flight plan can be copied into the secondary flight plan. The flight plan is copied and the secondary flight plan is displayed. Any changes made to the secondary flight plan will be saved but not activated. In addition to the secondary flight plan, secondary performance can also be entered. This allows the flight crew to input data for a secondary runway or secondary approach. To activate the secondary flight plan, select the Activate Secondary prompt. The secondary flight plan, including the secondary performance, is now active. Pressing the Direct key displays the Direct To page. This page allows you to navigate directly to any waypoint by entering the identifier in the Direct To field. Selecting the Direct To prompt will delete all flight plan waypoints between your present position and the Direct To waypoint. Radial in and radial out choices are also available. This can be useful when joining airways before a waypoint or the final course during approaches. To assist with situational awareness, abeam points can be selected. By selecting the Abeam Points prompt, an abeam waypoint displays at all flight plan waypoints between the present position and the Direct To waypoint. This allows the flight crew to continue to monitor aircraft fuel usage and en route time. In either case, inserting the waypoint will navigate the aircraft directly to the selected waypoint. Selecting the airport key will direct you to the bottom of the flight plan, typically the destination airport. Pushing the ATC COM key switches control of the MCDU to the ATSU subsystem. If ATSU is not installed, pushing the ATC COM key displays the MCDU menu page. Let's take a closer look at how data is entered on the MCDU. Amber boxes indicate a required data entry field. This data is required for the FMS to operate correctly and calculate predicted data. Brackets indicate the entry is optional. Information generated by the FMS is displayed in a small font, while pilot-generated information is displayed in large font. Certain information must be entered in a specific order. For example, Flight Plan Page A shows computed speed and altitude values for each waypoint. Speeds are listed first, with altitudes to the right. To enter an altitude constraint, you must precede the entry with a slash. This tells the system to enter the data into the field to the right of the slash. As an example, ATC directs you to cross the Janesville VOR at 13,000 feet. If 130 was not preceded by a slash, it would be entered as a speed constraint instead of an altitude constraint. That is incorrect. 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 That is correct. That is incorrect. That is incorrect. That is correct. That is incorrect. That is correct.